Hello everyone, this is Ali Beheshti. I'm an assistant professor of mechanical engineering and the director of Tribology and Surface Mechanics Lab at George Mason University. I would like to briefly talk about our research interests and activities in the lab. Our research generally focuses on tribology, which is the science of wear, friction, and lubrication. And in particular, we work on high temperature materials, additive manufacturing for extreme environments, indentation and scratch, as well as several surface engineering techniques like laser shock peening. I would also like to show you some of our projects and capabilities.
Let me briefly talk about some of our current research projects. One of the projects we have been involved in focuses on high temperature helium tribology of nickel alloys for high temperature gas cooled reactors. In fact, Department of Energy seeks to deploy its Generation 4 reactors with near zero carbon emission around 2035, where these advanced reactors will operate at very high temperatures near 1000 C, which is very challenging for surface reliability and performance of their components. Our work in particular involves both experiments and numerical simulations across scales. As you can see, for example, we perform nano indentation, and also we performed macro scale testing like friction and wear, trying to come up with predictive design formulas and recommendations for reactors licensing. On the second project, we use laser shock peening to enhance mechanical property of advanced alloys. As you can see here, laser shock peening uses laser to generate supersonic shock waves into the material and creates enhanced microstructures with high compressive residual stresses. Since its deployment, laser shock peening has saved billions of dollars, as it can significantly increase fatigue, wear, and corrosion resistance in lots of components, including aerospace and naval applications. In particular, here we currently study laser shock peening to understand the stability of the phenomena in high temperatures. Working with our collaborators, we develop novel hybrid thermal engineering and laser peening to increase fatigue and wear resistance at elevated temperatures. Specifically, for example, our preliminary results showed a 70% reduction in friction and wear for nickel alloys at 800 C using this novel hybrid technique. In another project, we investigate surface integrity of additively manufactured or 3D printed metals. These samples are made using direct metal laser sintering technique. As you can see in the animation, the samples are made of powders that are melted layer by layer through a laser beam. This technique actually can make prototyping super easy and also can create complex shapes. For example, a turbine blade with advanced cooling channels can be made here. However, due to the nature of the process, the mechanical and surface strength are lower compared to the rod counterparts. And in many applications, including aerospace and other applications, mechanical components are susceptible to a form of contact damage called fretting, which can result in drastic failure in the component. This actually makes the adoption of additive manufacturing technique challenging, especially for mission critical components like airplane, turbine blade. One of our concentration here is currently on studying multi-scale, high temperature fretting, wear, and fatigue of super alloys made through metal 3D printing. I would like also to mention a couple of instruments that we currently have in the lab. We have profilometer to measure surface topography with high resolution. We also have multi-scale indenter and scratch instrument that can precisely measure local mechanical properties down to submicron. At meso to macro scale, we have actually an advanced tribometer for measuring friction and wear in several configurations and up to 1000 C temperature. In addition, using the fatigue machine in Dr. Amuni's lab, we recently designed a special fixture to simulate high temperature freighting fatigue of mechanical components. For further information, please visit our website at tsm.vse.gmu.edu. I'm happy to answer your questions, and thanks a lot for your attention.